Hello everyone. So this is the heart rate prediction using electrocardiography project. The file mentioned is actually in the EDF format, which contains the raw ECG data, and it has been collected using the BTM sensor. So the MATLAB read EDF code basically opens that particular file, and after reading the code, we'll just plot it using the inbuilt matplot. We can clearly see that the data which we have is really noisy in nature. Hello everyone. So this is the
the first phase of the project was to find the position of all the R peaks. To do this, we needed to determine regions of interest for each R peak in the signal. We were mostly concerned with the intervals between the heartbeats and how they vary over time. And the way we approached this whole problem was that we had a twofold approach to the whole problem. The first solution was to generate more peaks, and this function is basically responsible for generating more peaks. We basically wanted to determine the slope between each set of points, and the next function basically calculates the beats per minute. And as we are scrolling down through the code, the other approach taken by us was the sliding window approach. So in this case, the window size was basically specified by the start and end interval. The n interval was basically a result of frequency multiplied by window size. Also, the window size is provided as a configurable parameter in the config_parser.ini file, which is located in the Python code base. And so this is the predict bradycardia.py file. So in this file, basically whatever the output, the CSV files are basically generated by the annotate.py, and for each corresponding dat file we have a CSV file, and this CSV file basically contains all the important metrics, which includes average R variance, and other columns. Next, we have the function, which is the predict bradycardia function. This function is responsible for predicting whether a label is can be classified as a bradycardic event or a non-bradycardic event. As you can see, we are having some sort of range in which if we have the average R which falls within, then we try to classify it as a bradycardic or non-bradycardic event. Then we have some important calculation parameters, for which we have this calculate accuracy function. In this function, what we are trying to do is we are trying to calculate some important metrics like true positive, true negative, false positive, false negative. Also, we are looking at some of the precision parameters, recall and accuracy parameters. So this is the annotate.py file. We have these utility functions. So the output, which is generated by the peakfinder.py file, which is the rpeaks.dat, which basically contains all the peaks, R peaks. This file basically takes as input the rpeaks.dat file, and it tries to calculate the beats per minute. And the function basically as you can see, this function is returning the beats per minute, the peak list which was calculated, and the RR list which was basically taken as input to this function. Now we come to the annotation part. So as mentioned in the project, we are doing manual annotation. So as you can see that once we find that the heart rate index is less than the threshold, we try to annotate and append ones or zeros. Next function is the get heart rate statistics. In this function, what we are trying to do is get some valuable statistics like the sum, the average, the variance, and what we are trying to calculate is basically the variance, and as you can see from the code, we are calculating the variance based on each peak value that we get in the array. Once we have calculated all the important metrics, we try to display whether it's a bradycardic patient or non-bradycardic patient. We also try to annotate the average R data, and it's based on the same logic as the way we were annotating before. The next important part is the pre-bradycardic condition, and as explained in the paper also, we are taking into account for the events that basically help in triggering this event of bradycardia. Also, we are trying to plot, and this is the main function from which the whole code base gets executed.
We basically have a config.ini file where we have specified the file name, the parameters such as frequency, window size, skip samples, threshold, and minute window, and other things like peak finder as well as. So we have basically created an Android app which can enable the users to check for bradycardia condition in patients. So we've declared the parameters as we had in the config file. Similarly, the variables for the button and text view are declared in the code, and using the metrics which we calculated from the Python code, we are basically trying to implement that in Java and then detecting whether the person has bradycardia or not. So initially what we do is we load the annotated CSV file by reading the contents which we have, like by after doing the manual annotations. So after that, using the initial condition of bradycardia, which is an average heart rate less than 60, we try to predict if the patient has bradycardia or he doesn't. So after deriving and detecting the bradycardia, we are basically trying to evaluate the accuracy of our conditions in terms of TP rate, FP rate, and other metrics such as F1 rate. So now if you can go in the assets folder, you can basically see the CSV files, where you can basically see all the annotated data, and the conditions are again specified in the config file. Finally, if you run the code and then when you see the emulator, you can basically see that we have an option of choosing between different patients. So now if I click on patient B, you can see that all the metrics are shown here, and the app also predicts whether the person has bradycardia or he doesn't. So we have basically created